Imagine waking up one day to realize that everything you've ever known, every planet, star, galaxy, and even time itself might have once not existed at all, and more bewilderingly, could have emerged from a state of absolute nothingness, a void devoid of matter, energy, space, and even the laws that govern them. This idea, as outrageous as it may sound, is not merely a fantasy born from science fiction, but a question that has puzzled humanity for millennia and now sits at the very heart of modern physics and cosmology. The concept of something emerging from nothing challenges the deepest intuitions we hold about cause and effect, existence and non-existence. Yet, some of the brightest minds in science have seriously grappled with this enigma, proposing profound theories that push the limits of our understanding. At the center of this puzzle lies the Big Bang, the moment our universe began to expand from an incomprehensibly hot and dense state nearly 13.8 billion years ago. But contrary to popular belief, the Big Bang doesn't explain what caused the universe to exist, it only describes what happened immediately after it started expanding, leaving a veil of mystery over what, if anything, came before. Quantum mechanics, the strange and probabilistic theory that governs the behavior of particles at the smallest scales, suggests that empty space is not truly empty at all, but instead seethes with quantum fluctuations, tiny, temporary bursts of energy that pop in and out of existence without violating the laws of physics. Some scientists have proposed that a sufficiently large quantum fluctuation in a primordial vacuum could give birth to an entire universe, with inflationary theory expanding this bubble into the vast cosmos we inhabit today. This idea reframes nothing as not a literal void, but a quantum vacuum governed by physical laws, where space, time, and even particles are emergent phenomena, not prerequisites. Yet that raises a further question: where did the laws themselves come from? If the universe can emerge from a vacuum, we must ask what mechanism defines that vacuum and why it follows the rules it does. The mystery deepens when considering the role of time itself, which may not have existed before the universe. In some models, such as the Hartle-Hawking no-boundary proposal, time transitions smoothly from a spatial dimension, meaning there was no singular moment of creation, no point where time started ticking, but instead, a rounded origin without a sharp beginning. This concept stretches our understanding of causality, forcing us to rethink what it means for something to begin, or for anything to exist at all. Meanwhile, the theory of cosmic inflation, proposed by Alan Guth and others, explains how the early universe expanded faster than the speed of light, ironing out any irregularities and creating the large-scale structure we observe today. But it also opens the door to the idea of a multiverse, an infinite or near-infinite number of universes, each emerging from its own inflationary event, making our universe just one of many bubbles in a grand cosmic foam. In such a model, the creation of universes could be a natural, even inevitable, consequence of the physics of the vacuum, where quantum fluctuations continuously spawn new realms with varying physical constants, dimensions, or laws. Other radical theories, like those rooted in string theory or loop quantum gravity, explore the idea that the universe is composed of tiny vibrating strings, or quantized space-time units, and that higher dimensions beyond our perception might play a critical role in the creation process, possibly involving collisions between massive membrane-like structures, brains, in a higher dimensional space, each impact sparking a new Big Bang. This would imply our universe is not an isolated incident, but a consequence of a deeper, more complex reality that defies conventional imagination. While these ideas are captivating and grounded in mathematical models and observational support such as the cosmic microwave background and large-scale structure, they still leave fundamental questions unanswered. Why do the physical constants have the values they do? Why is there a universe at all instead of nothing? These questions bridge the gap between physics and philosophy, with some scientists like Lawrence Krauss arguing that the laws of quantum mechanics alone are sufficient to allow universes to arise from nothing, while others counter that the existence of physical laws presupposes a framework that itself demands explanation. Even if we accept that something can emerge from a quantum vacuum, we must confront the origin of that vacuum, the meta-laws governing it, and why anything should exist in the first place. Some propose that perhaps the universe is a mathematical structure, a self-existing entity defined by logic and necessity, rather than contingency, while others suggest we may never fully understand the ultimate origin, because it lies outside the realm of empirical testability. And yet, with every observation we make, from the redshift of distant galaxies to the delicate imprints left on the fabric of the universe, by primordial sound waves we inch closer to peeling back the layers of the cosmic onion, daring to confront questions once reserved for religion and metaphysics using the tools of science. Technologies like the James Webb Space Telescope are now peering into the earliest moments after the Big Bang, offering unprecedented detail and challenging existing models with surprising discoveries, like the unexpectedly mature galaxies that seem to have formed earlier than current theories predict, possibly hinting at unknown dynamics in the early universe or flaws in our understanding of cosmic timelines. As our instruments grow more powerful and our theories more refined, we find ourselves on the threshold of a new Erewhon, where the line between something and nothing blurs, and where the question of how the universe emerged might not be a matter of belief but one of discovery. Whether the final answer lies in multiverses, quantum foam, higher dimensions, or something we haven't yet imagined, the search for how everything began continues to be one of the most exhilarating and humbling pursuits of human knowledge. The fact that we can even contemplate these questions, let alone develop testable hypotheses and mathematical frameworks around them, is a testament to the power of human curiosity and the unyielding drive to understand our place in the cosmos. As we stand on this pale blue dot orbiting an average star in a quiet corner of an unremarkable galaxy, we are perhaps the universe becoming aware of itself, peering into the abyss, not just to know how we got here, but to comprehend the very fabric of reality, to understand why there is something rather than nothing, and to embrace the possibility that the answers, however elusive, might forever alter the way we see ourselves and the infinite mystery that surrounds us. For most of human history, our understanding of the universe was shaped by mythology, religion, and direct observation of the sky, as ancient civilizations looked upward and crafted stories to explain celestial movements and cosmic origins, often attributing them to gods or supernatural forces. The Babylonians, Egyptians, Greeks, and Chinese all developed early forms of astronomy, using rudimentary tools and keen observation to track stars, planets, and the movements of the sun, day, and moon. But their interpretations were bound by geocentric models, most notably the one proposed by Claudius Ptolemy in the 2nd century, which placed Earth at the center of the universe, a view that would dominate Western thought for over 1,000 years. This worldview was eventually challenged during the scientific revolution, when Nicholas Copernicus, in the 16th century, proposed a heliocentric model where the planets, including Earth, orbited the Sunday, sparking a profound shift in cosmological understanding that was further advanced by the observational work of Galileo Galilei, who used a telescope to discover moons orbiting Jupiter and phases of Venus, both of which contradicted geocentrism. Johannes Kepler refined the heliocentric model with his laws of planetary motion, while Isaac Newton's formulation of universal gravitation in the 17th century laid the groundwork for a mechanistic, mathematically governed cosmos, where celestial bodies followed predictable laws. Over the next 2 centuries, improvements in telescopes and scientific instrumentation allowed astronomers like William Herschel and Edwin Hubble to peer deeper into space, revealing that the universe was far more vast and dynamic than previously imagined. Hubble's landmark discovery in the 1920s that galaxies are receding from us and that the universe is expanding overturned the long-held assumption of a static cosmos and gave birth to modern cosmology, paving the way for the Big Bang Theory, which proposes that the universe originated from an extremely hot and dense singularity around 13.8 billion years ago. This paradigm shift was supported by key discoveries such as the cosmic microwave background radiation detected in 1965 by Arno Penzias and Robert Wilson, which offered compelling evidence for a hot, dense origin and has since become a cornerstone of Big Bang cosmology. Throughout the 20th century, milestones in physics and astronomy such as Albert Einstein's general theory of relativity, which redefined gravity as the curvature of space-time, and the development of quantum mechanics, which introduced the probabilistic nature of particles and energy at microscopic scales further, enriched our understanding of how the universe behaves on both cosmic and subatomic levels. In tandem with theoretical advances, space exploration marked a new era of direct observation and experimentation beyond Earth, beginning with the launch of Sputnik by the Soviet Union in 1957, followed by human spaceflight with Yuri Gagarin in 1961, and culminating in the Apollo 11 moon landing in 1969, achievements that not only expanded technological capabilities, but also inspired a broader quest to understand humanity's place in the cosmos. Subsequent missions such as the Voyager probes, launched in 1977, provided unprecedented data on the outer planets and have now entered interstellar space, continuing to transmit information that enriches our models of the solar system and beyond. The Hubble Space Telescope, launched in 1990, revolutionized our view of the cosmos by capturing breathtaking deep-field images of distant galaxies, some of which are seen as they existed just a few 100 million years after the Big Bang, while instruments like the Planck satellite have mapped the cosmic microwave background in exquisite detail, allowing scientists to measure the age, composition, and shape of the universe with remarkable precision. As our models evolved, so did the concept of the observable universe, which refers to the region of space from which light has had time to reach us since the beginning of cosmic expansion, a sphere with a radius of approximately 46.5 billion light-years, beyond which we cannot currently observe due to the finite speed of light and the ongoing expansion of space itself. This notion emphasizes the limits of human observation while suggesting that the actual universe may be far larger, possibly infinity, and even home to regions governed by different physical laws or existing in completely separate frameworks, ideas that underpin modern theories of the multiverse and cosmic inflation. In recent years, the launch of the James Webb Space Telescope has opened new frontiers in cosmology by enabling astronomers to peer further into the past, observing galaxies from the earliest epochs of the universe, and providing data that may either confirm or challenge current models, especially concerning the nature of dark matter, dark energy, and the formation of structure. The historical arc of humanity's quest to understand the universe is a journey from myth to mathematics, from geocentrism to relativity, and from philosophical speculation to precision cosmology, revealing a cosmos that is not only vast and ancient, but also deeply mysterious, with each new discovery raising even more profound questions about origins, purpose, and the ultimate fate of everything we know. Imagine standing alone beneath a clear night sky, the stars spread above you like a silent ocean of light, and feeling a humbling stillness that stops time a moment, where your breath catches, not just from the beauty, but from the haunting realization of how vast the universe truly is, and how small you are within it. This is not just stargazing. This is an awakening, a confrontation with the unknown that stirs a deep, primal part of our minds that still dares to ask, where did all of this come from? Why is there something rather than nothing? And what, if anything, does it mean for me, for us, for humanity? In that instant, the universe isn't just a distant concept, it becomes personal. It touches on the most intimate fears and hopes, on mortality, purpose, meaning, and the very nature of existence. People should care about this story, not because they're scientists or philosophers, but because to be human is to wonder, to question, to seek meaning in the face of the unknowable. We are storytelling creatures, born to explore, driven by curiosity, and constantly reaching for answers beyond the horizon of what we currently know. The question of how the universe came to be from nothing is not just an abstract mystery, it is the greatest mystery, the ultimate origin story, and it includes all of us. From the atoms in your hands to the photons bouncing off your eyes as you read this, every part of you was born from the heart of stars and the deep processes of cosmic evolution, forged in a universe that may have erupted into existence from absolute void. What could be more profound than knowing that? And what could be more terrifying? Because wrapped in that awe is fear of insignificance, fear of being alone, fear that our entire existence is just a blip in a cold, indifferent cosmos. The void does not care if we love, or hurt, or dream. It will go on expanding long after we are gone, swallowing galaxies in its endless stretch, rendering the brightest stars into whispers of heat and darkness. And yet, that same void, that cosmic silence, also cradles something astonishing: life, consciousness, you. The fact that the universe could give rise to beings capable of looking back at it and asking where it came from is nothing short of miraculous. That is not just science, that is poetry. We are the universe becoming aware of itself, and that awareness is both a burden and a gift. It is what makes us yearn to understand black holes and cosmic microwave radiation, not because we need the facts to survive, but because our souls ache to feel connected to something larger than ourselves. We are meaning makers, and in the cold vacuum of space, we light our way, not just with equations, but with wonder. Children look up at the stars and feel it instinctively before anyone teaches them about light years or redshift. There is a magic in the unknown sense that somewhere out there is something grand and sacred and true. That feeling never really leaves us. It just gets buried beneath routine, beneath jobs and deadlines and traffic, until something image from a space telescope, a question from a child, a quiet night alone reminds us again that we are part of something incomprehensibly vast. When we ask how the universe came from nothing, we are really asking something deeper. Do I matter in the face of all this? Is there meaning in this dance of galaxies and atoms? Is there a reason? These are existential questions that no scientific formula can fully answer, but the pursuit of those answers is itself meaningful. It connects us to every human who ever looked up and wondered, from ancient priests charting the stars to modern scientists mapping the cosmic microwave background. Across time and culture, this question has united us, driven us, defined us. And the beauty is, we don't have to understand everything to be moved by it. The mystery itself is part of the gift. Not knowing is what compels us to search, to imagine, to push against the boundaries of what we think is possible. The cosmos is not just a sentence, it's a character in our human story, mysterious and indifferent, but also wondrous, majestic, and full of potential. Every new theory, every new observation is a breadcrumb on a trail that might one day lead to understanding who we truly are. Not just biologically or physically, but cosmically. This is not about escaping into science fiction or metaphysics. This is about finding belonging in the real world, about realizing that the atoms in your body have traveled across time and space, that you are the product of stars, of explosions, of gravity and chance and time and mystery. You are a fragment of the infinite. Thinking about the infinite, even the fear of being lost in this immensity, is part of what makes the journey worthwhile. Because in confronting the darkness, we discover light. We build telescopes to stare deeper into space. We write symphonies and stories to make sense of our place in it. And we hold each other tighter, knowing how precious life is in a universe that doesn't promise anything. This question, this mystery, is what binds the scientist to the poet, the philosopher to the child. It's what makes people cry at rocket launches and gasp at images of galaxies thousands of light years away. It's what drives us to send spacecraft beyond the solar system, with golden records of our songs and stories, messages in bottles to the stars. Because we care deeply, not just about the facts, but about the meaning, the emotion, the wonder behind those facts. So when we ask how the universe was created from nothing, we're not just looking for a scientific theory, we're expressing our deepest longing to know where we came from, where we're going, and whether we're alone. In a time when the world can feel fractured and distracted, this cosmic perspective offers unity, humility, and hope. It reminds us that we are all passengers on the same fragile rock, floating through the same incomprehensible mystery, writing our own small chapter in the story of everything. And maybe that's why we keep looking up, not because we're lost, but because we've always known, deep down, that the answers we seek out there are also the ones we're trying to find within. What if everything you believed about reality, about time, space, matter, even existence itself, was only a small part of a much larger, stranger truth? What if the universe, the vast cosmos that stretches beyond imagination, came into being not from something, but from nothing, not metaphorically, but in the deepest, most literal sense imaginable? Would that change the way you see the world, your life, your place, in the grand tapestry of everything? These aren't just abstract questions for scientists in lab coats. These are questions for all of us, because at the heart of this cosmic mystery lies something deeply personal, our understanding of what it means to be, to live, to exist. And right now, more than ever, we are standing at the edge of a new frontier, in thought one that could completely rewrite our view of reality. But we can't walk into that future alone. We need to ask, together, and keep asking, what is reality really made of? Can time exist without matter? Can space exist without time? Could something be born from true nothingness, or is nothing itself just a human concept? A word we invented for what we don't yet understand? These questions strike at the core of everything we think we know. Because if the universe can be born from nothing, if space and time can emerge spontaneously, then maybe the laws of physics as we know them are not eternal truths, but emergent phenomenarials of a game that began to exist when the game itself was created. And if that's the case, then the implications ripple out through every part of our lives. What is consciousness? Is free will real, or an illusion shaped by particles dancing to quantum rhythms? Are we unique, or is life a cosmic entity? Suddenly, questions that once felt like the domain of religion or philosophy are now being explored in labs and observatories, backed by data and mathematics, yet still rich with emotional and existential weight. Every discovery peels back another layer of the unknown, revealing a deeper puzzle, and behind that puzzle, more questions. Why should you care? Because this isn't just about telescopes and theories. This is about you, your story, your future, your mind, made of matter that once belonged to stars, now trying to understand where it all began and what lies ahead. When we discuss the idea of something coming from nothing, we're not just speculating about distant events, we're testing the limits of our own understanding. Imagine, just for a moment, that we discover definitive proof of how the universe began, not from divine intervention or an infinite past, but from a quantum event, a spontaneous fluctuation in a field we barely understand. How would that reshape education, belief systems, how we teach our children to think about existence? What would that do to our sense of awe, our sense of purpose? Would it make life feel meaninglesser, more miraculous than ever before? The future of this mystery isn't just about answering where the universe came from. It's about changing the way we interact with reality itself. As we learn more about the early universe, about quantum mechanics, about multiverses, about emergent laws, we begin to glimpse a world where time may not be linear, where space may not be fundamental, and where everything we consider real may actually be a projection or a vibration from deeper, hidden dimensions. Now imagine being part of that conversation, not just as a passive observer, but as an active thinker, a questioner, someone who brings their own thoughts and emotions into the dialogue. Because science doesn't progress in silence. It progresses through voiced out discussion, creativity, and passion. What do you believe about the origin of everything? Do you think the universe had a beginning at all, or is it part of a never-ending cycle? Could multiple universes exist, each born from its own variation of nothing? And if so, is our universe rare or common? Is it finely tuned for life? Or is life simply adapted to the settings it was given? These are not questions with easy answers, and that's the point. These mysteries invite us into the process of discovery. They encourage debate, not just among scientists, but among artists, philosophers, students, and dreamers. They belong to all of us. And as new tools like the James Webb Space Telescope, quantum simulators, and even AI-driven models begin to uncover data from the earliest epochs of existence, the pace of discovery will only accelerate. We may be on the brink of understanding how dark matter works, or what dark energy truly is, or what the vacuum of space contains beneath the Planck scale, but none of that will matter unless we can feel its importance, unless we talk about it, question it, share it. You don't have to be a physicist to be part of this. You just have to be curious. Ask yourself, when I look at the night sky, do I feel wonder or fear? Does knowing how small we are make life feel less meaningful or more precious? Do you believe science will one day answer everything? Or are there mysteries that will remain forever out of reach? The beauty of this mystery is that it is unfinished. Every question you ask, every hypothesis you consider, becomes a part of the collective human story as species, trying to understand the infinite from a tiny blue dot in the corner of a galaxy. And in that effort, we discover something extraordinary. That knowledge doesn't reduce wonder, it deepens it. The more we learn, the more we realize how much we don't know. That gap, the unknown, is not a flaw in our understanding. It's an invitation, an open door, a sign that the universe is still speaking, still waiting to be uncovered. So don't just read about it, talk about it. With your friends, with your children, with your community. Watch the sky and wonder what you're seeing. Read about quantum fields and imagine what they feel like. Watch a black hole simulation and ask yourself what it means to vanish beyond an event horizon. Because ultimately, this is more than a scientific journey. It's a human one. We don't explore the cosmos just to collect data, we explore it to find ourselves. And the mystery of how the universe came from nothing, that's not just the first chapter in a story. It's our story, one that is still being written, question by question, discovery by discovery, dream by dream. So what will your part be in that story? What will you question? What will you imagine? What will you share with the next generation who looks up and asks, where did all this come from? The next great leap in understanding may come from a labor. It may begin with a conversation sparked by wonder. Either way, it begins now, with you. Imagine drifting slowly through the infinite quiet of space, where no wind blows, no birds sing, and no ground exists beneath your feet. There is no up or down, no center or edge, just an endless sea of darkness, illuminated by ancient starlight. A galaxy spins in the distance, like a glowing pinwheel, suspended in nothing, its arms stretching for hundreds of thousands of light years, filled with hundreds of billions of stars, each one potentially orbited by planets, some of which may cradle life looking up in wonder as we do. Nebulae bloom like cosmic flowers, vast clouds of gas and dust sculpted by stellar winds and shockwaves, their colors ranging from brilliant blues to deep reds, glowing with the promise of new stars yet to be born. Beyond them, interstellar voids yawn, regions so empty that a grain of sand would be lonely, yet even here, gravity whispers, and the faint signature of dark matter tugs silently at the cosmos. This is the stage of our story, the setting of all things, the backdrop to every moment in the history of existence. It is as silent as it is sublime, and as cold as it is breathtaking. Space, contrary to its name, is not just empty, it is rich with structure, governed by forces that shape the visible and the invisible alike. And it invites us not only to observe, but to feel. Drift deeper, and you'll encounter massive clusters of galaxies bound together by gravity into colossal webs stretching across the observable universe. These are not mere clouds of stars, but gravitational cities where cosmic drama unfolds. Galaxies collide in slow-motion ballets, sending shockwaves through gas clouds, igniting new waves of star formation. These collisions can take billions of years, and yet to us, frozen in our brief human timescale, they appear timeless, like a painting suspended in the stillness of the cosmic void, and behind it, a lurking unseen, undetected by any telescope as dark matter. It neither emits nor absorbs light, yet it makes up more than 80% of the matter in the universe. We know it exists only by how it bends the paths of galaxies and stars, its ghostly presence felt in the movements of objects far too fast for their visible mass. Even stranger is dark energy, a force driving the universe apart, accelerating its expansion as if space itself is stretching at the seams. We don't know what it is, but we know it's everywhere, in every direction, pushing the fabric of the cosmos outward toward an unknown fate. These are the phenomena that fill the silence of space, not with noise, but with mystery. And within that mystery, a community of brilliant minds continues the quest to understand what it all means. These are the architects of our cosmic knowledge, as scientists, whose imaginations reach as far as their equations. Stephen Hawking, whose work on black holes and the boundaries of space and time gave new shape to questions once reserved for theologians. His concept of Hawking radiation reshaped how we think about the fate of information in the universe. Albert Einstein, who rewrote the rules of gravity, showing us that mass bends space and time. and in doing so, opened the door to modern cosmology. Edwin Hubble, who looked through his telescope and realized that the galaxies were moving away from us, that the universe was expanding. Vera Rubin, who studied the rotation of galaxies and provided some of the strongest evidence for dark matter. Alan Guth, the father of cosmic inflation, who theorized that the universe underwent a rapid exponential expansion in the earliest moments after the Big Bang. And today, names like Brian Greene, Sean Carroll, Lisa Randall, and Neil deGrasse Tyson carry the torch, making the vastness of space understandable to the public, while researchers at observatories, particle accelerators, and space agencies push the frontiers of what we know. Their work is not simply scientific, it is profoundly emotional. They are not just solving problems, they are exploring the unknown with childlike wonder and relentless curiosity. To them, a data anomaly can be a doorway to a new law of nature. A faint wobble in a star's motion can hint at an unseen planet. A flicker of microwave radiation can carry echoes from the dawn of time. This sense of exploration, of venturing into uncharted territory, defines the spirit of cosmology. It's not just about collecting facts, it's about asking again and again what lies beyond, and having the courage to pursue the answer even when the path is uncertain. This atmosphere, the grand, unshakable vastness of the cosmos, paired with our fragile determination to understand, it creates a tone that is both humbling and electrifying. Awe and mystery are the dominant forces here, but they are not paralyzing. They inspire action. They motivate questions. They make us feel small, yes, but in the best way possible. Because in recognizing our smallness, we also recognize our uniqueness. Out of all the known matter in the universe, we are the rare phenomenon that can ask questions about its origin. We are not separate from the universe. We are the universe made of stardust, structured by the laws of physics, animated by consciousness. That is not a poetic metaphor. It is a literal truth, one that makes every human moment part of a far grander story. And this story isn't finished. Right now, new observatories, like the James Webb Space Telescope, are peering further into the universe than ever before, capturing light that has traveled for over 13 billion years. We are seeing galaxies from the earliest chapters of cosmic history, challenging existing models and hinting at new physics. Meanwhile, researchers at CERN are probing the smallest particles of matter, looking for clues about the forces that shaped everything, while theorists grapple with ideas like string theory, loop quantum gravity, and the possibility of multiple dimensions. We are on the cusp of revelations that could transform how we understand time, space, and the very nature of existence. Every new discovery is not just a scientific victory, it's a cultural one, a human one. It changes the way we think, the way we feel, the way we dream. So picture it again, that vast, dark canvas scattered with stars, full of invisible forces and hidden structures, humming with energy we can barely comprehend. It is not empty, it is alive with mystery. And in that silence, in that grand cosmic stillness, our questions echo like music. What came before the Big Bang? What lies beyond the observable universe? Is there an edge, a center, a purpose? Could our universe be one of many? Could reality itself be far stranger than we've ever imagined? These questions don't have easy answers, but they are the lifeblood of curiosity, the engine of progress, the fuel of wonder. As you move through your day, surrounded by the ordinary, remember this: above you, beyond you, stretching in every direction, is a cosmos more vast, more mysterious, and more beautiful than anything we've yet imagined. And you are part of it. Not a visitor, not an outsider, but a thread in the fabric, woven from the same elements as stars and galaxies. Thinking, questioning, dreaming. That is the true atmosphere of the cosmos, not just space and matter, but feeling. Not just facts, but fascination. In the end, science doesn't just tell us what is. It invites us into the great unfolding story of the universe, not just to understand, but to feel it. To stand at the edge of the infinite, and in awe, take one more step. The deeper we gaze into the universe, the more it begins to look like a hall of mirror stone that reflects not just stars and galaxies, but also the boundaries of our knowledge, our tools, and perhaps even the limits of what is knowable. From the earliest whispers of cosmic expansion to the bizarre behavior of quantum particles, every new layer we uncover seems to carry with it not just answers, but contradictions, paradoxes, and doors we may never fully open. This is the quiet conflict at the heart of modern cosmology, that the closer we come to understanding everything, the more we realize how little we may ever truly grasp. There are signs everywhere that suggest we might be approaching a horizon not just of observation, but of comprehension, and that some truths about the universe may be fundamentally inaccessible to human minds, not because of a lack of intelligence or effort, but because reality itself may not be fully revealable to beings living within it. The concept of an edge to the universe is already more metaphorical than literal. When we talk about the observable universe, we refer to the portion of the cosmos from which light has had time to reach us since the beginning of the cosmic expansion. Beyond that, we can only guess. The universe may be infinite, or it may loop back on itself in a higher dimensional way. But either way, the expansion of space ensures that regions beyond a certain distance will remain forever hidden, their light never reaching us, no matter how long we wait. This is not just a technical barrier. It is a fundamental horizontal boundary of causality beyond which information is lost to us forever. And if we can't see it, measure it, or interact with it, can we ever say we know it? Even within the observable universe, the story becomes more tangled the deeper we dig. Consider quantum mechanics, where particles exist in probabilistic states, capable of being in multiple positions at once until observed. This bizarre behavior leads to paradoxes like Schrödinger's cat and entanglement, where two particles, even separated by galaxies, seem to influence each other instantly. These effects, confirmed by experiment, defy our classical understanding of space, time, and causality. Then there's the infamous measurement problem. What does it mean for a particle to be observed? Does consciousness play a role in collapsing the wave function? Or is there a deeper, hidden mechanism we've yet to uncover? Even with all our equations and experiments, quantum theory remains, at its heart, not fully understood. On the largest scales, general relativity beautifully explains gravity and the curvature of spacetime, predicting black holes and gravitational waves, both of which we have since observed. But when we try to combine relativity with quantum mechanics, the result is mathematical chaos. The theories don't harmonize. At singularities, like the center of a black hole or the beginning of the universe, our equations break down. They return infinity S signals that the math has entered a realm where it no longer describes physical reality. These singularities are more than just theoretical nuisances. They are warnings, clues that we are missing a deeper layer of reality, one that no current theory can adequately describe. And then there's dark matter and dark energy, terms that feel more like placeholders than explanations. We know dark matter must exist because galaxies rotate in ways that visible matter alone cannot account for. But we don't know what it is. Is it a particle, a field, a flaw in our understanding of gravity? And dark energy is even more elusive. It makes up roughly 70% of the universe, driving its acceleration, but its nature remains completely mysterious. These are not small gaps in our knowledge. They are gaping holes, suggesting that the true architecture of the universe may lie hidden behind veils we don't yet know how to lift. Even the concept of time, so central to our experience of reality, begins to dissolve under scrutiny. In relativity, time is flexible. It stretches and compresses depending on speed and gravity. In quantum physics, time doesn't even appear. In the same way, it's not a fundamental property, but an emergent one. Some cosmologists suggest time might be an illusion, a side effect of entropy and memory, a structure we project onto the universe to make sense of cause and effect. If time itself is not what we think it is, then how can we ever truly understand beginnings, origins, or before? And if we can't define a clear beginning, how can we ever hope to answer the question of how something came from nothing? Layered over these conceptual dilemmas are our observational limitations. We build more powerful telescopes, launch spacecraft, and peer further than ever into the past, but we are still confined to a single vantage point. We can't step outside the universe to see it from the outside. Every observation we make is shaped by our position in spacetime, our instruments, and even our biology. Our brains evolved to track movement through forests and social relationships, not to comprehend the geometry of 11 dimensions or the behavior of quarks. Yes, we use math as a bridge, a language that seems to reflect the universe's inner logic. But even math may be incomplete. Gödel's incompleteness theorem proves that no system can be both complete and consistent, and that might apply to the very laws of physics themselves. As we pursue grand unified theories and frameworks like string theory or loop quantum gravity, we find ourselves faced with beautiful, elegant equations and no experimental way to test them. String theory proposes tiny vibrating strings in 10 or more dimensions, but these strings are so small we can't currently detect them. Multiverse theories suggest infinite other universes, but if they are causally disconnected from our own, how could we ever know they're real? The danger here is not that these theories are wrong, but that they may be permanently untestable, that we may be approaching a limit, a point where we can still ask questions, but can never confirm the answers. This growing uncertainty is not a failure of science. It's a testament to its honesty. Science doesn't offer comforting final answers. It offers testable, falsifiable models of reality. It tells us when those models no longer work. That honesty is powerful, but it's also sobering. It means accepting that some questions might not have clear answers. It means embracing the possibility that the true nature of the universe may remain partially hidden, not just for now, but forever. And yet, that tension, that conflict between curiosity and constraint is what makes this journey so compelling. We are driven by the desire to know, even when we suspect we may never fully succeed. The paradoxes, the contradictions, the edges we can't cross, they are not dead ends. They are signposts, guiding us toward new ways of thinking, new tools, new theories. They remind us that the map is not the territory, and that the cosmos may always contain mysteries deeper than we can currently imagine. So we ask, what happens at the edge of a black hole? Can we reconcile gravity and quantum physics? Are we living in a universe that had a beginning or one that is part of an eternal cycle? Do we have the cognitive tools to answer these questions? Or will we, like ancient mariners at the edge of a medieval map, forever wonder what lies beyond the known, comforted and haunted by the phrase, "Here be dragons"? Perhaps the greatest conflict is not between theory and data, or between general relativity and quantum mechanics. Perhaps it is between what we want the universe to be: understandable, complete, logical, what it is, vast, unpredictable, and laced with enigma. That conflict is not a flaw. It's the beating heart of discovery. And as long as we keep asking, keep building, keep dreaming, we will remain in the most important position of all. Not as masters of the universe, but as its most devoted students. In the grand theater of cosmology, where minds are stretched across eons and equations span the edges of comprehension, a deep and unresolved conflict simmers just beneath the surface zone that pits theory against observation, elegance against evidence, and intuition against paradox. This is not a conflict of egos or personalities, though the history of science is full of passionate debates. It is a deeper, more philosophical struggle at the heart of modern physics. The tension between our competing visions of the universe's origin, structure, and fate. From the very first moment humanity realized the stars were not fixed on a dome above us but were distant suns scattered across an unfathomable void, we've been seeking not only to measure the cosmos, but to understand it. Yet, as our tools and knowledge have grown, so too has the complexity of the questions we face. And now, at the cutting edge of science, we find ourselves caught in a fundamental discord. The universe, it seems, refuses to be easily defined. One of the most profound points of tension lies in the effort to define the edge, if such a thing exists. Does the universe have an edge, a boundary, a limit beyond which there is nothing? Or is it infinite, stretching on forever in all directions? Or perhaps it is finite but unbounded, like the surface of a sphere, which loops back on itself without a true edge. Each of these possibilities is supported by different models and interpretations of data, but none can yet claim complete certainty. The problem is not just observational, it's theoretical. In general relativity, the universe can be curved in various ways, positively like a sphere, negatively like a saddle, or flat like an infinite plane. Current observations suggest the universe is nearly flat, but nearly leaves room for both infinity and large-scale curvature, that we haven't yet observed. Inflation theory, which explains the universe's rapid early expansion, predicts flatness with high probability, but it also leads to models where the universe is just one bubble among countless others in an eternally inflating multiverse scenario that, while mathematically compelling, may be forever untestable. This leads directly into the struggle between observational evidence and theoretical elegance. Cosmology thrives on models' beautiful, intricate mathematical descriptions that try to make sense of reality. But the more complex our models become, the more they outpace our capacity to confirm them. The multiverse, for instance, is not just a science fiction fantasy. It arises naturally from inflationary theory, string theory, and quantum mechanics. Yet, by definition, other universes are beyond our observational reach. If we can't ever see them, test them, or interact with them, are they part of science or philosophy? This is where the conflict turns inward, forcing the scientific community to confront its own boundaries. Should we continue building theories that may never be falsifiable? Or should we focus only on what can be seen and measured? Theoretical physicists, like Brian Greene and Max Tegmark, argue that a broader, more abstract view is needed, while experimentalists warn against venturing too far into the unobservable, where theory becomes speculation. Another front in this conflict lies in reconciling the two pillars of modern physics, general relativity and quantum mechanics. Relativity explains the large-scale structure of the universe, gravity, black holes, the curvature of space-time, while quantum mechanics governs the micro-world of particles and probability. Both are incredibly successful within their domains, but they are mathematically incompatible. Attempts to unify them, such as string theory and loop quantum gravity, have produced elegant frameworks but no definitive answers. The problem is especially acute when discussing the beginning of the universe. The Big Bang singularity, where space and time are thought to have emerged, represents a point where both theories must apply simultaneously, but neither can operate alone. This creates a dead zone at the most important moment of cosmic history, a paradoxical place where our best tools fail us completely. Some propose the universe began as a quantum fluctuation. Others suggest it has always existed in some form. Each model has implications for whether the universe is finite or infinite, whether it began with a bang or is part of a larger cycle. And yet, no model has yet emerged as definitive. Cosmologists are not just caught between theories, they are caught in the grip of the data itself. Take the current tension between measurements of the Hubble constant, the rate at which the universe is expanding. Observations of the early universe using the cosmic microwave background, CMB, give a different value than observations of nearby supernovae and galaxies. The discrepancy is small in absolute terms, but statistically significant, and it suggests that something fundamental in our model may be missing. Is there a new form of energy or physics we haven't accounted for? Are we misunderstanding the properties of dark energy? Or is there a flaw in how we interpret the data? This is not an academic puzzle. It's a foundational issue, one that could reshape our understanding of the universe's age, structure, and destiny. And while we face contradictions between models, we also struggle with the limits of what we can know at all. The observable universe, for example, is limited by the speed of light and the age of the cosmos. Beyond about 46.5 billion light-years, light hasn't had time to reach us. That means we are forever confined to a bubble of visibility, a cosmic island surrounded by unknowable territory. If the universe is larger, we cannot see it. If it has a shape or a boundary, we cannot touch it. This is not a flaw of technology, it's a law of nature. And that makes the job of cosmologists even more daunting, to describe a whole they cannot observe, using parts they can only measure indirectly. Even the very concept of nothing, central to many origin theories, is under conflict. In classical terms, nothing is the absence of everything. But in quantum mechanics, nothing is a seething foam of probabilities, where particles can appear and disappear without cause. Some cosmologists propose that our universe came from such a quantum vacuum, spontaneously born through a fluctuation. But this nothing still obeys physical laws that must somehow have existed before the universe began. Where did those laws come from? If nothing is not really nothing, can we ever define a true beginning? Or are we chasing a concept that only appears to make sense from within our limited framework? Within all these tensions lies the emotional heart of the conflict, the human need for closure in a universe that may never provide it. We want a beginning, a cause, a reason. We want a structure we can understand, a map with borders, a theory of everything that wraps it all into one neat, elegant equation. But the universe may not cooperate. It may be messier, more infinite, more paradoxical than we are comfortable admitting. It may hold truths that are beyond what any species limited by space and time can ever know. And that possibility that we might be permanently barred from knowing the full truth is what makes this conflict so profound. And yet, cosmologists press on. They compare equations, build simulations, launch telescopes, and argue at conferences not out of arrogance, but out of a passionate belief that some deeper coherence must exist, that there is a layer of truth beneath the paradoxes, a synthesis yet to be found. The struggle between finite and infinite, between observation and theory, between relativity and quantum mechanics, this is not a sign of failure. It is the friction of progress. It is how science moves. Every contradiction is a clue, every breakdown an opportunity. The universe, in refusing to be simple, invites us to rise to its level, not to conquer it, but to align ourselves with its complexity, to embrace the uncertainty and keep asking questions. This conflict, the one at the center of cosmology, is not something to be resolved quickly. It is a story still unfolding, a drama that has stretched from the moment the first humans looked at the sky and will continue as long as intelligence endures. Whether the universe is infinite or finite, whether time had a beginning or loops eternally, whether space is flat or curved, we may never reach the final answer. But in the search itself, in the passionate, tireless pursuit of understanding, we find something just as important: a reflection of ourselves. The universe may be chaotic, paradoxical, even unknowable, but we are its children, and in our struggle to comprehend it, we become part of its story. A story shaped not by certainty, but by courage, the courage to keep exploring, even when the map dissolves into stars. If the universe has no edge, if it is infinite in extent or loops back on itself in ways that defy ordinary comprehension, and everything we know about space, time, and matter must be reevaluated, such a possibility is not just a theoretical footnote. It is a turning point in the history of thought, a paradigm shift with consequences that ripple far beyond equations and observatories. The implications for physics and cosmology are profound. If there is no boundary, no edge where the universe stops, then the traditional notion of a central origin point begins to collapse. The Big Bang, long thought to be the beginning of everything, may not be a singular event from nothing, but merely a phase transition in an eternal cosmos. The universe may have always existed in one form or another, perhaps evolving through cycles, or bubbling forth endlessly in a multiverse, where our own cosmic bubble is just one of countless others. In such a view, the search for a definitive beginning or a final edge becomes meaningless, not because it's unimportant, but because it doesn't exist in the way we imagined. This demands more than new models. It requires a transformation in how we even ask questions about the universe. Traditional cosmology is based on boundaries, initial conditions, space-time coordinates, observable horizons, but what if these are only artifacts of our limited perception? The absence of an edge challenges the idea of a finite universe and raises questions about total energy, entropy, and the applicability of conservation laws on a cosmic scale. In an infinite universe, standard thermodynamics begins to break down. If the cosmos has infinite energy, infinite matter, infinite space, then what does it mean to calculate averages or speak of evolution? How do we model a universe where everything that can happen does happen, possibly an infinite number of times? From a philosophical perspective, the implications are staggering. For centuries, humanity has drawn comfort and identity from being part of a story with a beginning, a middle, and an end. Religion, literature, art all are structured around the concept of narrative boundaries. But an infinite universe, it offers no closure, no edge to approach, no final chapter. This raises an unsettling possibility. What if the universe simply is, with no cause, no purpose, no arc? Such a realization can feel dizzying, even terrifying, stripping away the mythic framework that has long helped humans find meaning. But it can also be liberating. In a universe without edges, our lives are not defined by outer limits, but by inner depth. Meaning is not handed down from a cosmic architected, must be forged, discovered, created. This existential shift mirrors the scientific one. An edgeless cosmos forces us to move beyond traditional physics into new conceptual terrain. General relativity and quantum mechanics were revolutionary, but their unification has eluded us for over a century. If we are to understand a universe without edges where space and time may be emergent, and where geometry might arise from deeper principles, need a new framework entirely. This is the motivation behind quantum gravity, string theory, holography, and other speculative models. These aren't just mathematical games. They are attempts to construct a language adequate to the reality we're beginning to glimpse. In some of these models, space and time are not fundamental at all, but arise from entanglement, information flow, or deeper structures we haven't yet fully conceptualized. The universe could be holographic in nature, where the information on a lower dimensional boundary gives rise to the higher dimensional reality we experience. But if there is no boundary, no edge, what does the hologram project from? What is the base layer of reality? These questions push physics into territory once reserved for metaphysics. What is real? Is the universe a computation, a simulation, a mathematical structure? If it has no edge, then perhaps it has no fixed center, either nothing to anchor it. We may have to abandon cherished ideas like locality, causality, and even identity as we develop tools to describe a cosmos with no frame. This doesn't mean surrendering rigor. On the contrary, it demands even greater precision, creativity, and openness from the scientific community. It means rethinking what evidence is when dealing with an infinite system, where rare events can happen infinitely often, and statistical norms may be impossible to define. Another consequence of a boundless universe is the redefinition of uniqueness. In an infinite cosmos, anything that can happen not only will happen, but will happen again and again. There may be infinite versions of Earth, of you, of this very moment, unfolding with slight variations or identical repetition. This challenges not only science, but identity, ethics, and the meaning of individuality. If your consciousness is not unique, but one of countless instantiations, how do we define selfhood? If the universe never ends, are we part of a single story or one of endless overlapping narratives without a main plot? This may sound like science fiction, but it arises naturally from many inflationary and quantum models that permit infinite configurations in an eternal multiverse. Moreover, the absence of an edge reshapes the search for answers itself. If there is no beginning, no ultimate boundary, perhaps there is no final theory, either just better approximations, ever more refined models. Physics may become more like cartography, mapping regions without ever capturing the whole. This is not defeat, it is maturity. Accepting that the universe may always retain mystery is not surrender, it's the embrace of humility in the face of cosmic immensity. Science, in this sense, becomes a practice of curiosity, a discipline of the unknown, a way of dancing with questions rather than crushing them with answers. And yet, even in the face of boundlessness, the human response is not despair, it is wonder. An infinite universe inspires awe. It encourages us to ask not only, what is out there, but why can we even ask? Our ability to reason, to reflect, to measure and model a reality of such staggering scale is itself miraculous. We are the product of this edgeless universe, shaped by its laws and mysteries, yet somehow capable of glimpsing its shape. That glimpse may be partial. It may always be partial, but it is no less beautiful for its incompleteness. So what happens now? We go forward. We build better telescopes, launch deeper missions, develop more precise detectors, and write bolder theories. We look for signatures of new physics, quantum fluctuations at the Planck scale, gravitational waves from the dawn of time, patterns in the cosmic microwave background that might hint at a pre-Big Bang reality. We debate, we simulate, we dream, And we do so knowing that every discovery brings new questions, that the absence of an edge is not the end of science, but its greatest challenge and its greatest promise. In the end, the consequences of an edgeless universe are not only scientific, they are spiritual, intellectual, emotional. They ask us to live in a world that may never yield final answers, and to find joy and meaning in the asking itself. They call us to be seekers, not of ends, but of endlessness. Because in a universe without boundaries, the true frontier is not out there in space. It is here, within, using our courage to wonder, to explore, and to love the mystery we may never solve. There comes a moment in every great story when everything changes, a discovery that reframes everything. A shift so fundamental that it splits time into before and after. In the story of the universe, this moment came not with a single experiment, but with a sequence of revelations that began quietly, almost invisibly, yet ultimately altered the trajectory of cosmology forever. The 20th century opened with Einstein's general theory of relativity, a framework that reimagined gravity not as a force, but as the curvature of space and time caused by mass and energy. With it, the universe itself became dynamic, capable of expanding, contracting, curving, even beginning and ending. But at that time, the prevailing belief among great thinkers was that the universe was static, eternal, unchanging. Einstein himself introduced a cosmological constant into his equations, a sort of anti-gravity term, to keep the universe from collapsing under its own gravity. It was a mathematical trick, later regretted, and yet the idea behind it would come back in a way he never expected. Then came the discovery by Edwin Hubble in the 1920s that galaxies were not only moving away from us, they were doing so in a pattern that indicated the entire universe was expanding. This alone changed everything. No longer could we imagine the universe as an infinite, eternal stage. Instead, it had a historia beginning. This was the dawn of the Big Bang Theory, a model that described the universe as having emerged from an unimaginably hot and dense state roughly 13.8 billion years ago. As this model grew, it was reinforced by powerful evidence. The cosmic microwave background radiation, CMB, discovered accidentally by Arno Penzias and Robert Wilson in 1965, provided a fossil imprint of the early universe, proof that it once glowed with heat and has since cooled as it expanded. But even as these revelations solidified a coherent picture of cosmic history, a new and unexpected twist arrived at the end of the 20th century, one that would become the turning point in cosmology. In 1998, two independent teams of astronomers, observing distant Type Ia supernovae, made a startling discovery. The universe's expansion was not slowing down. As everyone expected from gravitational attraction, it was accelerating. Something was pushing space apart faster and faster. This force, this mystery, came to be called dark energy. And its implications shattered what we thought we knew. If gravity should slow expansion, what could be strong enough to reverse that? What was this repulsive pressure permeating all of space? And what did it mean for the ultimate fate of the cosmos? Suddenly, the cosmological constant, once Einstein's biggest blunder, returned with new relevance. In modern cosmology, it serves as a candidate for dark energy, suggesting that even empty space contains energy of vacuum energy that drives expansion. But why? Why does the vacuum have this property? Quantum field theory predicts vacuum energy vastly greater than what we observe be 120 orders of magnitude, the worst mismatch in physics. This gaping discrepancy is not just a curiosity. It's a sign that something is deeply wrong or incomplete about our understanding of reality. Dark energy now accounts for about 70% of the total energy density of the universe, and yet we have no idea what it really is. This isn't just a mystery, it's the defining problem of modern cosmology. Meanwhile, technological advancements have been racing to catch up with theory, opening new windows to the cosmos. The Hubble Space Telescope, launched in 1990, allowed humanity to peer into the deep past, capturing galaxies as they appeared billions of years ago. Its images weren't just beautiful, they were revolutionary. Hubble's deep field views showed galaxies forming earlier and more abundantly than expected, pushing astronomers to rethink the speed and structure of early star and galaxy formation. Then came gravitational wave detectors like LIGO and Virgo, which in 2015 confirmed Einstein's prediction that space-time itself could ripple like a pond disturbed by a stone. For the first time, we were not just seeing the universe, we were hearing it. But it was the James Webb Space Telescope, JWST, launched in late 2021, that pushed the boundaries in unprecedented ways. With infrared capabilities far beyond Hubble's, JWST was designed to see the first stars and galaxies, the cosmic dawn just a few hundred million years after the Big Bang. And its early findings shocked the scientific community. Galaxies appeared more mature, more massive, and more structured at earlier epochs than models predicted. Some galaxies were forming stars at rates that defied expectations, and their shapes and metallicities hinted at complexities in cosmic evolution not yet understood. These weren't merely observational anomalies, they were potential signs that our theories of early galaxy formation, star formation, and even the age-structure relationship of the universe may need to be revised. Even more startling were early hints that the expansion rate, measured from the early universe via the CMB and baryon acoustic oscillations, does not match the expansion rate inferred from nearby galaxies. This Hubble tension may be a statistical fluke. It could be the signature of new physics, such as changes in dark energy over time, modifications to gravity, or the influence of exotic particles. Each possibility would fundamentally alter our model of the universe, indicating that we may be standing on the edge of a second cosmological revolution. This turning point isn't just technical, it's philosophical. Science is beginning to ask, are the constants we take as fundamental actually variable? Are the laws of physics themselves emergent properties, shaped by a deeper underlying system? Is dark energy a clue to quantum gravity? Could it be a field, a particle, an illusion, or a misunderstanding? And what about the idea of inflation, that brief moment after the Big Bang when the universe expanded faster than light? Inflation explains many features of the universe's large-scale structure, but new data from JWST and Planck have raised questions about its fine-tuning, prompting some theorists to explore alternatives like bouncing cosmologies or string-based origins. These questions signal more than a challenge, they mark a pivot. We are no longer just refining the details of a known framework. We are being invited, perhaps, for to consider that our entire understanding may be too narrow, too anthropocentric, too rooted in visible matter and classical thinking. And this is where the true beauty of the turning point lies. It does not destroy science. It deepens it. It pushes scientists out of certainty and into creativity. It asks for new ideas, new minds, new frameworks. We are not done mapping the universe. We are at the beginning of the next chapter. So here, we stand on a planet orbiting an average star in a typical galaxy, looking back through space and time with instruments of glass, metal, and mathematics. We've discovered that the universe is expanding, and that this expansion is accelerating. We've learned that most of the universe is made of things we cannot see: dark matter, dark energy, unknown particles. We've heard the echoes of the Big Bang in the microwave sky. We've watched black holes collide in distant galaxies. And we've seen galaxies form at a pace that defies our predictions. Every one of these discoveries is a signpost. Every one is a spark. And together, they form the firelight of a new era where physics and cosmology must grow beyond their current limits. In the face of such awe, our response must be both humble and bold. We must be humble enough to let go of cherished models when the evidence demands it. And we must be bold enough to imagine new realities, to ask wild questions, to challenge the foundations of knowledge. Because this is the turning point, not the end, not the edge, but the beginning of a deeper journey into the unknown forces shaping reality, into the architecture of space and time, and into the heart of what it means to be a conscious part of this living, mysterious, expanding universe. What if the problem isn't the universe, it's us? Not because we're not smart enough or persistent enough, but because we might be looking at reality through the wrong lens. For centuries, we've tried to understand the cosmos by treating it like a giant machine, measurable, local, and deterministic. Space and time were fixed backdrops. Particles had positions and velocities, and the goal was to discover the laws that govern them, like Newton's apple falling with predictable elegance. But with every revolution relativity, quantum mechanics, dark matter, dark inner reality, has pushed back, as if to say, you're not seeing the full picture. And now, in the wake of puzzling discoveries and paradoxes that resist traditional explanations, a new idea is emerging, not just a new theory, but a new perspective that could redefine our entire understanding of the cosmos. One of the most provocative proposals to emerge from the edge of theoretical physics is the holographic principle. It suggests that the three-dimensional universe we experience, including space and time, might be a projection from a two-dimensional surface, much like a hologram. This isn't science fiction. It's grounded in real theoretical work, especially in attempts to unify quantum mechanics and gravity. The idea gained traction after studies of black holes revealed something bizarre. When matter falls into a black hole, the information about that matter appears to be preserved not inside it, but on its surface, the event horizon. Jacob Bekenstein and Stephen Hawking showed that a black hole's entropy, a measure of its information content, is proportional not to its volume, but to its surface area. That's counterintuitive. We're used to thinking that more volume means more room for information, more complexity. But in black hole sand, possibly the entire universe, it's the boundary, not the bulk, that holds the key. This insight led to the bold suggestion that everything we perceive in 3D space, including movement, time, and even gravity, might be emergent phenomena illusions generated by deeper rules inscribed on a distant, lower dimensional boundary. This is the core of the holographic principle, and it has profound implications. If true, it means that space is not fundamental. Time might not be fundamental. They might arise from entangled quantum states, from correlations between bits of information encoded on a surface we cannot directly perceive. Think about that for a moment. Reality as we know, it could be like a 3D movie projected from a 2D film strip. We live inside the image, not the projector. These ideas have been mathematically explored in string theory and quantum gravity, especially in the context of the anti-de Sitter conformal field theory, ADS, CFT, correspondence, developed by Juan Maldacena. In this framework, a universe with gravity in a certain type of curved space, ADS, can be exactly described by a quantum theory without gravity on its lower dimensional boundary, CFT. It's like saying every object, every force, every phenomenon in our space, including gravity itself, could be encoded in a more abstract, flat space without gravity. This blows open the door to reinterpret what fundamental means. Could it be that we're confusing the output of the simulation with its code? That everything we call real is the byproduct of informational dynamics playing out at a deeper level? These shifts in perspective are not trivial. They reshape the questions we ask. Instead of asking where space came from, we ask what creates the illusion of space. Instead of asking how time began, we ask what processes give rise to our experience of time. Quantum mechanics, long treated as a set of weird rules confined to the atomic scale, suddenly becomes the architecture on which reality itself is built. The very weirdness of quantum physics entanglement, non-locality, superposition may not be bugs in the system. They may be features, the foundational threads from which the universe is woven. Consider entanglement, the phenomenon where particles become so deeply linked that the state of one instantly affects the state of another, no matter how far apart they are. Einstein called it spooky action at a distance, but it's been confirmed countless times in the lab. What if space itself is the result of entanglement? Some physicists, like Mark van Ramsdonk and others, have proposed that the geometry of space-time emerges from the entanglement structure of quantum systems. In this view, space is not a container, it's a pattern, and when entanglement decreases, space shrinks. When it increases, space expands. In this model, a tear in the fabric of space could correspond to a breakdown in entanglement. A black hole might be a region of massively scrambled information. Gravity? Perhaps not a fundamental force, but an emergent property of the way information flows across this structure. These are not just wild philosophical musings. They are part of a serious and growing conversation in theoretical physics. They offer a potential resolution to deep problems in unifying quantum mechanics and gravity. in explaining the entropy of black holes, in solving the so-called information paradox. They even touch on the nature of consciousness and observation. If the universe is made of information, what role do observers play in shaping it? Does consciousness collapse wave functions? Or is it itself an emergent property of quantum information flow? Such questions force scientists to cross traditional boundaries, to collaborate across physics, computer science, mathematics, even neuroscience and philosophy. And that collaboration is reshaping the scientific landscape. We are no longer just looking at particles in space. We're looking at networks, simulations, algorithms, and systems that exist outside the familiar boundaries of space and time. We're modeling quantum computers not just as machines, but as analogs for how the universe itself might work: probabilistic, non-local, entangled, information-driven. And in doing so, we're seeing the early outlines of a new kind of science, one that doesn't just describe the world as it appears, but explains why it appears that way at all. This shift in perspective also influences how we interpret observations. Take the James Webb Space Telescope, JWST, which is providing deep infrared views of the early universe. Its data are surprising researchers by revealing galaxies that appear older and more evolved than they should be, based on current models. But maybe the problem isn't the data, it's our framework. If space and time are emergent, then the speed at which structures appear might not reflect linear cause and effect. It could reflect deeper dynamics in the fabric of quantum entanglement. Similarly, our difficulties in detecting dark matter or explaining dark energy might stem from assuming these phenomena are particles or fields, when they may instead be signatures of emergent space-time geometry or even our incomplete understanding of how gravity behaves at cosmological scales. This doesn't mean we should abandon traditional science. On the contrary, it means we must expand it. A change in perspective is not a rejection of old models, but a layering of new understanding atop them. Newton wasn't wrong. His laws still describe how apples fall. Einstein wasn't wrong. His theory still describes how planets orbit and light bends. But now we may be on the edge of another leap, one where space, time, matter, and energy are no longer the base ingredients of reality, but the foam at the crest of a deeper quantum ocean. Ultimately, what we're witnessing is not the collapse of physics, but its transformation. The tension between general relativity and quantum mechanics, the conflict that has stymied physicists for a century, might only be resolvable by changing how we see everything. What if space-time is not the background, but the outcome? What if particles are not the starting point, but emergent patterns in a field of quantum information? What if the universe is not a place, but a process? This is more than a shift in theory, it's a shift in identity. If we are made of matter, and matter is made of quantum fields, and quantum fields are structured by information, then we are part of the code, part of the story, part of the holographic dance. The edge of understanding is not a boundary we will one day reach, it is the ever-expanding horizon that moves as we move, changes as we change. And that may be the most powerful insight of all, that science is not the search for final answers, but the practice of seeing more deeply, more clearly, through ever-changing lenses. So yes, we could be looking at the problem the wrong way, but maybe that's the point. Maybe the universe has been waiting for us to turn the map upside down, to stop searching for the edge and start exploring the structure beneath. Maybe the truth isn't out there. Maybe it's within the entangled, mysterious, ever-evolving quantum structure of the cosmos and of ourselves. Just when we thought we were beginning to grasp the shape of the universe, its origin, its trajectory, the rules that govern its unfolding reality, threw us an unexpected twist. A series of discoveries and theoretical developments in recent decades have not only defied our past assumptions, but shattered the illusion that we live in a single, comprehensible, self-contained universe. Instead, the cosmos may be far stranger than we imagined, more complex, more layered, and perhaps not even real in the way we once understood reality. These revelations aren't just adjustments to a model. They are tectonic shifts in our understanding of existence itself. And at the center of them is a question we never expected to ask so seriously. What if the universe we know is only one of many? Or worse, what if it's not real at all? The first sign of the twist came not from philosophical speculation, but from the cold, calculated predictions of inflation theory. Introduced by Alan Guth in the early 1980s, cosmic inflation solved key problems in the standard Big Bang model: why the universe looks so flat, why it is so uniform across vast distances, and why it contains tiny fluctuations that would eventually grow into galaxies. But inflation didn't stop at solving problems. It created new ones. According to many models of inflation, once this rapid expansion begins, it never really stops. Pockets of space continue inflating eternally, while small regions like our own observable universe bubble off and slow down, forming universes with potentially different physical constants, laws, and structures. This is not an optional add-on. It's a mathematical consequence. Eternal inflation leads directly to the multiverse, a vast ensemble of universes, most of which we will never see, all born from the same quantum foam. For a long time, the idea of a multiverse was dismissed as untestable, even heretical. But the data didn't go away. If inflation is true, then the multiverse may be unavoidable. String theory, another major candidate for unifying quantum mechanics and gravity, reinforced this idea by suggesting that there may be 10 circumflex 500 possible vacuum states, each corresponding to a different version of physical reality. In this landscape of possibilities, our universe may just be one valley among countless others. The constants we observe, such as the strength of gravity or the mass of the electron, may not be fundamental, but environmental. We live in a universe that allows life simply because we couldn't be asking the question from any of the ones that don't. This anthropic reasoning, once viewed with suspicion, has become increasingly hard to ignore. Why is dark energy so small, yet non-zero? Why does our universe permit complexity? Why does it appear to be fine-tuned for life? The multiverse doesn't explain these facts directly, but it reframes them. In a cosmic lottery of infinite outcomes, life emerges in the rare pockets where the settings are just right. We may be the winners of this impossible odds game, not by design, but by selection bias. We are here because we can be here. And just as we began to digest the implications of the multiverse, another, even stranger idea emerged from the realm of theoretical physics and digital technology: the simulation hypothesis. Popularized by philosopher Nick Bostrom and echoed by technologists like Elon Musk and scientists such as Neil deGrasse Tyson, the simulation hypothesis proposes that what we perceive as the universe may not be a base reality at all. Instead, it could be a sophisticated simulation run by an advanced civilization, or perhaps by nature itself. The idea is deceptively simple. If it's possible to simulate a universe down to the quantum level, and if such simulations are easier to run than to create original universes, then simulated realities might vastly outnumber real ones. Statistically, it becomes more likely that we are in one. This doesn't mean we're trapped in a video game, but it does mean that our assumptions about causality, physics, and even time may be deeply flawed. We might be part of a system with embedded rules, rendered for observers, driven by algorithms we cannot perceive. Our experience of reality could be a user interface designed to hide the underlying complexity of the code. In such a model, quantum randomness might be a feature of computational limitations. Entanglement could be a shortcut in the system's architecture. Space could be an illusion for managing data relationships. If that sounds absurd, remember, some of our best models already describe the universe in terms of information, not matter. In quantum mechanics, particles are described by wave functions' probability amplitudes. In black hole physics, information is never destroyed, only scrambled. In holographic models, the three-dimensional world is a projection from two-dimensional data. In all of these frameworks, reality begins to look more like a computation than a construction. This may sound like science fiction, but it's being taken increasingly seriously because of how well it aligns with emerging insights in physics. For example, the growing recognition that space-time itself may be emergent, not fundamental, but the byproduct of quantum entanglement has given new life to the idea that reality might be programmable. The same equations that describe error correction in quantum computing are now being used to describe the geometry of space. In other words, what we see as continuous space might be the emergent result of an underlying quantum circuit working to preserve coherence. That's not a metaphor. It's a mathematical reality being explored right now in the frontiers of quantum gravity. If all of this is true, if we live in a multiverse, or a simulation, or an emergent holographic structure, then the implications are staggering. First, it means we have to abandon the idea of a single, coherent, self-contained reality. There may be many realities, many versions of real. What we call the universe may be only one layer in a much larger meta-reality. Second, it means we may never be able to understand everything from within. If you're inside the system, you may not have access to the source code. There may be limits, not just to what we know, but to what we can know. But perhaps the most profound realization of all is this: our place in the cosmos is not diminished by these revelations, it is deepened. To know that we are not at the center of a single, stable universe, but are participants in a vast, evolving, possibly infinite structure, does not make us small. It makes us extraordinary. We are the rare instance where consciousness has arisen to reflect upon its origins. We are the simulation aware of itself, the hologram studying its own light, the quantum pattern asking why. This is not the end of meaning. It is a transformation of it. It also means that science must expand not in ambition, but in perspective. We must learn to ask questions that don't assume a single outcome or a singular truth. We must explore probabilistic realities, test for traces of alternative geometries, search for signatures of digital artifacts in physical law. We must become comfortable with layers of truth, with the idea that physics might describe how things appear, while something deeper explains why they appear at all. Already, researchers are devising tests, however tentative, for the simulation hypothesis. Some are looking for computational limits in cosmic rays. Others are exploring anomalies in entanglement. Still more are asking whether certain constants like the fine structure constant might show quantized behavior, as if emerging from discrete code. These are not easy tests. They may not yield quick answers, but they represent a new kind of science zone that dares to challenge not just what we know, but how we know it. And this brings us full circle. For most of history, humanity saw itself as the center of the cosmos. Then we learned we were orbiting a star on the edge of a galaxy in an expanding universe. Now, we're learning that the universe itself may not be the whole story. There may be no center at all, only context. And in that context, we are not the passive observers of a given reality, but active participants in a mystery that transcends space, time, and even logic. So what is the unexpected twist? It's not just that the universe may be part of a multiverse, or that we may be living in a simulation, or that space and time are illusions. The twist is this: our understanding of the universe has become inseparable from our understanding of ourselves. The boundary between physics and consciousness, between matter and meaning, between the cosmos and the questionnaires, vanishing. We are not outside the universe looking in, we are of it. And as we continue to peel back the layers of reality, we may find that the most profound discovery of all is not what we see in the cosmos, but what the cosmos sees in us. As we stand on the edge of what feels like a new scientific renaissance, where questions about the universe's origin, structure, and even nature are more sophisticated than ever, the path ahead is not one of smooth acceleration. It's strewn with profound challenges, technological limitations, and conceptual barriers that will require unprecedented innovation, collaboration, and vision to overcome. The revelations of the last few decades have not solved the cosmic puzzle. They've merely revealed how large, intricate, and perhaps incomplete the puzzle really is. For all the progress we've made in understanding dark energy, cosmic inflation, quantum gravity, and the potential multiverse, each answer has opened more doors than it has closed. Future research in cosmology, astrophysics, and theoretical physics now faces a daunting frontier that demands not only new tools, but entirely new ways of thinking. One of the most immediate hurdles facing scientists is the limit of observational reach. We are bound inescapably by the horizon of the observable universe, about 46.5 billion light-years in radius. Anything beyond this horizon, due to the expansion of space, lies permanently out of reach. No matter how powerful our telescopes become, we cannot receive light or signals from regions where cosmic expansion outpaces the speed of light. This presents a fundamental limitation to our understanding of the universe's true size, shape, and topology. Is the universe infinite? Is it curved like a higher dimensional sphere? Are there hidden structures beyond our horizon? We don't know, and in principle, we may never know. The best we can do is infer, simulate, and model. Even within the observable universe, we are limited by the resolution and sensitivity of our instruments. While the James Webb Space Telescope has revolutionized our view of the early universe, detecting galaxies that formed just a few 100 million years after the Big Bang, even JWST has its limits. It can't probe the Planck era, first fraction of a second after the universe's birth, where quantum gravity effects dominate. Nor can it observe dark matter or dark energy directly. These mysterious entities make up 95% of the universe, yet remain invisible to all electromagnetic instruments. Our understanding of them comes only through their gravitational effects. Show galaxies rotate, how the universe expands, how light bends. We are working from shadows on the wall, trying to reconstruct the shape of unseen players. This is why the next generation of space missions and observatories is so critical. Projects like the Nancy Grace Roman Space Telescope, the European Space Agency's Euclid mission, and proposed successors to JWST like LUVOIR, Large UV Optical IR Surveyor, or HABEX, Habitable Exoplanet Observatory, aim to peer deeper, measure more precisely, and search more broadly than ever before. Roman, for example, will survey large portions of the sky for evidence of dark energy's behavior across time. It will help determine whether this force is constant or dynamic, whether it strengthens, weakens, or evolves. These are not minor details. They could mean the difference between a universe that coasts forever and one that tears itself apart in a big rip. Even more ambitious are proposed missions to detect primordial gravitational wave ripples in spacetime from the very earliest moments after the Big Bang. Experiments like LISA, Laser Interferometer Space Antenna, or DECIGO, hope to capture the faint echoes of cosmic inflation, confirming or falsifying inflationary models that predict a multiverse. These missions will test the quantum structure of gravity, probing a realm where our current theories fall apart. If successful, they could help unify general relativity and quantum mechanics, perhaps the greatest open challenge in modern physics. Meanwhile, terrestrial experiments continue to push boundaries in particle physics, hoping to catch glimpses of the universe's invisible components. The Large Hadron Collider, LHC, has yet to find supersymmetry, extra dimensions, or particles of dark matter, but upgrades and future colliders, like the Future Circular Collider, promise higher energies and more precise measurements. Physicists also study neutrinos, axions, and other hypothetical particles that could explain dark matter, matter-antimatter asymmetry, or the universe's vacuum energy. These experiments are massive, delicate, and expensive, but they are essential for uncovering what lies beneath the standard model of particle physics. Yet tools alone are not enough. Many of the biggest challenges ahead are not technological, but conceptual. For example, reconciling quantum mechanics and general relativity remains unsolved, not due to a lack of effort, but because they operate on such radically different principles. Gravity, as Einstein described it, is smooth, geometric, and deterministic. Quantum physics, on the other hand, is grainy, probabilistic, and non-local. Attempts to unify them, such as string theory, loop quantum gravity, and causal set theory, have shown promise, but none have yielded experimentally testable predictions. We may need a radical shift in perspective, not just a unifying equation, but a new metaphysics, a way to think about space, time, and matter as emergent phenomena rising from something even more fundamental, perhaps something informational. This leads to another challenge: how to test ideas that may lie beyond current empirical reach. The multiverse, the holographic universe, the simulation hypothesis, these are all serious scientific ideas, but they stretch the limits of what can be observed or falsified. How do we evaluate models that propose unseen universes, higher dimensions, or reality as computation? This is not a failure of science, but a signal that our methodologies must evolve. We may need new frameworks for theory evaluation, ones that blend mathematical elegance, empirical plausibility, and philosophical coherence. We may need to redefine what it means for a theory to be scientific in a universe that resists full observation. And then there is the challenge of data. With telescopes, satellites, and particle detectors collecting petabytes of information, we face an overwhelming flood of data. Making sense of it requires not just human ingenuity, but machine learning, AI pattern recognition, and advanced modeling tools. Artificial intelligence will likely play an increasing role in helping scientists detect anomalies, identify hidden correlations, and even propose new hypotheses. But this brings its own risks. Data overfitting, algorithmic bias, or mistaking correlation for causation. The human touch curiosity, skepticism, imagination remains irreplaceable, even in a data-saturated age. Amid all these hurdles, one of the most critical needs is interdisciplinary collaboration. The future of cosmology will not be shaped by isolated geniuses, but by networks of thinkers, physicists, mathematicians, philosophers, engineers, computer scientists, and even artists working together to explore reality from multiple angles. New ideas often emerge at the intersection of fields. When someone asks a question that doesn't fit neatly into one discipline, what if space-time is a kind of entanglement structure? What if reality is a quantum computation? What if our theories of cosmology are incomplete because they exclude the role of consciousness or observation? These are boundary-pushing questions, and answering them requires a kind of scientific creativity that embraces uncertainty rather than fears it. Perhaps the most fundamental challenge of all is patience. The scale of the universe is not measured in meters, but in light years. The pace of discovery is not measured in months, but in decades, sometimes centuries. Galileo never saw the fulfillment of his vision. Einstein never saw gravitational waves confirmed. We must be willing to build knowledge, not for ourselves, but for the generations to come. This means funding long-term research, nurturing young scientists, and creating a culture that values slow, deep progress over fast, shallow breakthroughs. And through it all, we must stay humble. The universe has surprised us time and again, defying our expectations, challenging our intuitions, inviting us to think more deeply, more abstractly, more beautifully. From the moment we discovered the Earth was not the center of the cosmos, we've been on a journey not just outward, but inward. Each discovery about the universe teaches us something about ourselves, our place, our limits, our potential. The challenges that remain are enormous, but so is the adventure. And in every unanswered question, there is a promise that the story of the cosmos is far from finished, and we have much left to discover. So as we look ahead to new telescopes, new theories, new missions, and new mindsway, must remember, we are still at the beginning. The universe is vast, mysterious, and alive with secrets, and the greatest ones may still lie just beyond the horizon, waiting for the next bold step, the next improbable idea, the next generation who dares to ask, what if reality is deeper than we ever imagined? At the climax of any great saga, the final confrontation isn't just a battle between opponents, it's a reckoning with the unknown. In the grand story of humanity's quest to understand the universe, we now find ourselves standing on the edge of such a confrontation. After centuries of discovery, after Newton and Einstein, after Hubble and Hawking, after dark matter, inflation, and quantum fields, cosmology is no longer a confident march toward a final theory. It is a storm of competing ideas, each elegant in its own right, each powerful, and yet none able to claim victory. The dream of a theory of everything still drives the world's most brilliant minds, but the path to that unification is tangled, uncertain, and as vast as the universe itself. At the heart of this confrontation lie the latest competing theories of reality, with its own strengths, its own beauty, and its own unsolved paradoxes. Among the most promising contenders is string theory, a mathematical framework that reimagines the fundamental building blocks of the universe, not as point particles, but as tiny vibrating strings, whose oscillations give rise to everything we observe: electrons, quarks, gravity, and more. String theory's greatest achievement is that it includes gravity naturally, allowing quantum mechanics and general relativity to exist within a single, unified model. It also predicts extra dimensions, up to 11 in total, that may be compactified or hidden from direct observation. Yet for all its mathematical elegance, string theory struggles with testability. It offers a landscape of possible universes, possibly 10 circumflex 500 different configurations, without a clear mechanism for selecting the one we live in. It is a theory of everything and some fear of nothing in particular. Another major contender is loop quantum gravity, LQG, which takes a very different approach. Rather than treating gravity as a force within quantum fields, it attempts to quantize space itself. In LQG, space-time is composed of tiny loops woven into a discrete network called a spin foam. These loops are not embedded in space, they are space. This theory has the advantage of being background independent, aligning with general relativity's insight that space is dynamic, not fixed. LQG makes specific predictions about the quantization of area and volume, and it offers new ways of thinking about black holes and the early universe. But it lacks the unifying reach of string theory and struggles to incorporate matter fields and other forces. Its scope may be too narrow for the everything we seek. Then there are the emergent space-time models, where neither space nor time is fundamental. These theories draw heavily from quantum information theory, positing that space arises from entanglement patterns across quantum states. In this view, geometry is not built into the universe, it emerges from the structure of quantum correlations. The EREPR conjecture, proposed by Leonard Susskind and Juan Maldacena, suggests that wormholes, Einstein-Rosen bridges, are the geometric manifestation of quantum entanglement, Einstein-Podolsky-Rosen pairs. If true, this could unite two of physics' most mysterious concepts, black holes and entanglement, into a single language. The AD-CFT correspondence, meanwhile, provides a concrete example of a holographic universe where gravity in a higher dimensional space is equivalent to a quantum field theory in one fewer dimension. These ideas are tantalizing because they explain why space appears the way it does. But they rely on mathematical settings, like anti-de Sitter space, that don't match our real universe exactly. And translating these insights into testable physics remains a monumental task. While these theories continue to evolve, the debate over the boundary of the universe rages on not just physically, but philosophically. Will we ever find a true edge? If the universe is infinite, then there is no edge to find. If it is finite, but unbounded like the surface of a sphere loops back on itself, there is no outside. In such a model, asking what lies beyond is like asking what's north of the North Pole. The observable universe gives us a limit in practice, but not necessarily in principle. The boundary may not be a location in space, but a limit in time, the surface of last scattering, the Big Bang, the quantum foam at the Planck scale. And yet, even these boundaries are increasingly being questioned. The no-boundary proposal by Hartle and Hawking suggests that time itself becomes spatial at the origin, eliminating the need for a singular beginning. In a growing number of models, the beginning of time may be a Miragia point where classical concepts break down and must yield to quantum gravity. Still, the question persists: will we ever know for sure? Some scientists believe we are close to the final theory, that with a few more breakthroughs, we will unify all forces, explain all constants, and uncover the master equation of the cosmos. Others argue that the universe may be inherently unpredictable, fundamentally probabilistic, or even self-simulating, with no single underlying law, but a web of interacting frameworks. If we live in a multiversome of many universes, each with different laws than our final theory, may be a statistical one, an explanation of how our universe fits into the larger whole, rather than why it exists uniquely. If we live in a simulation, then the ultimate laws of our physics may be arbitrary constructs of a higher reality. These are not fringe ideas, they are part of mainstream conversations in cosmology, driven not by fantasy, but by necessity. The data are too strange, the models too diverse, the questions too profound to ignore them. As we confront these competing visions of the cosmos, the most urgent challenge remains the unification of general relativity and quantum mechanics. Every major theoretical effort, whether string theory, loop quantum gravity, holography, or something entirely new, is aimed at this reconciliation. General relativity describes the universe on the grandest scales: stars, galaxies, black holes, the expansion of space itself. It is geometric, continuous, and deterministic. Quantum mechanics, by contrast, rules the microscopic world: atoms, particles, fields, and forces. It is probabilistic, discrete, and non-local. Both theories work with astonishing precision in their respective domains, but when applied together, such as at the singularity of a black hole or the first instant of the Big Bang, they fail catastrophically. The equations collapse. The infinities explode. And in that chaos, we find the final confrontation of modern physics. The unification of these theories is not just a technical problem, it is a conceptual revolution. We may need to give up cherished assumptions that time flows uniformly, that space is continuous, that particles are fundamental. We may need to embrace ideas that are deeply counterintuitive, that reality is built from information, that the universe is a hologram, that gravity is not a force but a thermodynamic effect. This is the price of progress, and scientists are willing to pay it because the stakes are not just intellectual, they are existential. Understanding the true nature of the universe means understanding what it means to exist at all. And so we look to the future of cosmology. The next generation of telescope, space-based and ground-based, will peer deeper into the early universe, map the cosmic web, test dark energy, and search for primordial gravitational waves. New particle accelerators may reveal hidden symmetries or undiscovered particles. Quantum computing and AI may help simulate theories too complex for classical methods. And theoretical work will continue to push boundaries, searching not for the easiest answers, but for the ones that change everything. The final confrontation is not about proving one theory right and the others wrong. It is about discovering the larger framework in which they all make sense, where relativity and quantum mechanics are not rivals, but reflections of a deeper unity. Whether that unity is a set of equations, an informational structure, a computational process, or something beyond our current language is unknown. What is certain is that the journey is not over. The universe has not yet revealed its final secret, and perhaps it never will. But as long as we ask, as long as we wonder, as long as we stand beneath the stars and search for the edge of the cosmos, we are participating in something timeless, a dialogue between mind and mystery, between what is and what could be. In that confrontation between knowledge and the unknown, between elegance and complexity, between the dream of unification and the reality of paradox, we find not just science, but meaning. And that, more than any equation, may be the legacy of cosmology, not just to explain the universe, but to awaken us to the wonder of being within it. In the quiet of space, where stars burn silently and galaxies drift like cosmic islands across unimaginable distances, there is no voice to speak of, meaning only the soft glow of ancient light crossing eons to reach us. Yet here we are, tiny creatures on a pale blue dot, asking the biggest questions that existence allows. Where did we come from? What is all this for? Is there a boundary, a beginning, a purpose? In the face of the infinite, these questions might seem naive, but it is precisely our insistence on asking them that reveals something profound, not just about the universe, but about ourselves. For in exploring the unknown, we don't just gain facts, we gain wisdom. And that is the moral core of cosmic exploration. It expands more than our knowledge, it expands our capacity to wonder, to feel, to connect, and to grow. The deeper meaning of exploring the cosmos is not just about charting galaxies or discovering particles. It's about realizing our place in a story that is older, bigger, and more mysterious than anything we can fully comprehend. The atoms in our bodies were forged in stars. The water we drink was cycled through comets and planetary collisions. The light in our eyes was born in the same Big Bang that set galaxies spinning. To study the universe is to study the very matter of which we are made. But beyond this material connection lies a spiritual Oneia reminder that we are not separate from the cosmos, but an expression of it. We are the universe, thinking, asking, dreaming, and that dream has moral weight because it calls us to live in awe, in humility, and in harmony with the vastness that birthed us. At the center of this journey is curiosity, that spark that drives children to ask, why? That fuels scientists in lonely labs, that keeps philosophers awake at night staring at the stars. Curiosity is not a luxury. It is our species' most powerful tool for survival, transformation, and meaning. Without curiosity, we would still fear eclipses as omens, view the sky as a ceiling, and never have glimpsed the grandeur beyond our world. Every advancement from the wheel to the web, from fire to fusion, began with curiosity. And in science, curiosity is discipline, a commitment to question, to test, to be surprised, to remain open to truths we do not yet understand. But curiosity also demands balance, because in our hunger for knowledge, we can become arrogant, mistaking understanding for mastery or data for truth. The universe reminds us constantly that we know only a fraction of what there is to know. Dark matter, dark energy, quantum paradoxes, and the mystery of consciousness all whisper of how much lies beyond our grasp. This is not a cause for despair. It is a call to wonder. True wisdom lies not in having all the answers, but in learning to live with the questions honestly, humbly, joyfully. Knowledge and mystery are not opposites. They are partners in a dance that has guided humanity through the ages. One of the great lessons of cosmic exploration is that progress does not mean certainty, it means deeper complexity. Every time we peel back a layer of reality, we find more to explore. The atom was not the end of the road, it was a door to the quantum realm. The Big Bang was not the beginning, it was the start of a deeper mystery about what, if anything, came before. This is the beauty of science. It is not a fortress of facts, but a frontier of questions. And this frontier teaches us how to live, not just how to build better machines, but how to build better minds and better societies. From the cosmos, we learn perspective. The famous pale blue dot image, taken by Voyager 1, shows Earth as a speck of light suspended in a sunbeam mote of dust in a vast cosmic sea. From out there, all our divisions, our borders, our conflicts vanish. What remains is the fragile miracle of life. This awareness is not abstract. It has ethical weight. It calls us to stewardship, to compassion, to unity. When we realize how small and rare our planet is, how fragile its ecosystems, how interconnected its people, we begin to see that caring for Earth is not just ecological, it is existential. We have no other home, and perhaps no other chance. The cosmos also teaches us patience. Stars take billions of years to form. Galaxies drift across space in a slow dance that defies our clocks. Scientific discovery itself unfolds over decades, sometimes centuries. In a world obsessed with speed, instant results, and constant stimulation, cosmic time is a teacher of depth. It reminds us that some truths are worth waiting for, that wisdom grows slowly, that some questions may never be answered in our lifetime. But that doesn't mean we should stop asking. The pursuit itself is meaningful. The journey is sacred. And what of failure? Science is full of it. Hypotheses disproven. Experiments that yield no results. Observations that contradict theory. Yet, from failure, we learn. Cosmic exploration teaches resilience, the courage to be wrong, to revise, to start again. In this way, science mirrors life. We are not born knowing our purpose. We stumble, we guess, we grow. The moral lesson is clear. Value the process. Value the search. Value the courage to explore, even when the outcome is uncertain. But perhaps the most profound moral takeaway is this: we are capable of transcendence, not in the supernatural sense, but in the very real ability to reach beyond ourselves, our fears, our limitations, our divisions, and grasp something greater. The cosmos inspires us not just to think, but to feel, to experience awe, reverence, even love for a reality so vast it defies measure. This is not sentimentality. It is a form of spiritual realism. The same emotion that moves us to tears at a sunset, or a newborn's cry, or a glimpse of starlight that left its source before Earth even existed. That emotion is part of what makes us human, and it is necessary. Without it, science becomes cold, knowledge becomes sterile, power becomes dangerous. In this sense, the universe is not just a subject of study, it is a mirror. It reflects our values, our hopes, our limits, and our potential. And through it, we can learn to be more than what we were. We can learn to see the world not as us versus them, but as all of us together, adrift on a fragile world under the vast and ancient stars. We can learn to embrace diversity not just of cultures and ideas, but of perspectives and mysteries. We can learn to nurture curiosity, humility, courage, and compassion. These are not scientific values. They are human values, and they are the true fuel of discovery. So what lies at the heart of the universe? We don't know. Maybe we never will. But what lies at the heart of science, of exploration, of the human spirit? That we do know. It is the willingness to ask, to wonder, to search, even in the dark, to build a telescope, launch a probe, write an equation, and look up at the night sky not with fear, but with longing, with hope, with love. Because we are not separate from the universe. We are a way for the universe to know itself. And that is a sacred calling. In the end, the moral lesson of cosmic exploration is not that we will find all the answers. It's that we are worthy of the search. That we can rise above ignorance, pettiness, and fear. That we can build cathedrals of knowledge, even on uncertain ground. That we can hold space for both the known and the unknowable. That we can be humbled by what we don't understand and still be empowered to try. And maybe that's the ultimate gift of the cosmos, not just knowledge, but perspective. Not just facts, but meaning. Not just answers, but the reminder that to wonder is to be alive. That curiosity is a form of love. And that even in an infinite, mysterious, and often silent universe, the act of reaching out, of asking, of imagining, of exploring is itself a kind of light. One that may never end. As our journey through the universe draws to a close, the final question rises, like the sun over a distant world. Should the mystery remain open, ended? After all, we've explored the origins of space and time, the paradoxes of quantum mechanics, the vastness of the cosmos, the strange allure of multiverses and simulations, the elegant tension between theory and observation. There is a deep human desire to find closure. We want a final chapter, a complete explanation, a theory of everything etched into the fabric of certainty. But perhaps that's not what the universe is offering us. Perhaps its greatest gift is not in answers, but in the space to wonder. In that sense, the mystery should remain open not because we failed to solve it, but because the act of questioning is itself a vital part of what it means to be alive, conscious, and connected to the cosmos. To leave the mystery open-ended is not to surrender to ignorance. It is to embrace the beauty of the unknown with the full force of curiosity, humility, and imagination. The greatest thinkers in history, from Copernicus to Newton, from Einstein to Hawking, did not seek finality. They sought deeper understanding, and each time they succeeded, they opened more doors than they closed. In science, the unanswered question is not a dead end, it's a torch passed to the next generation. To leave questions unanswered is to affirm that we are part of an evolving story, one that no single mind, no single era can complete. It means accepting that some truths are not yet visible, not yet measurable, not yet ready. And that's okay, because the universe is not a riddle to be solved. It's a reality to be experienced, layer by layer, light year by light year. So what are the biggest takeaways from our exploration? First, the universe is far more complex, vast, and mysterious than we once imagined. From its potential birth in a quantum fluctuation to its expansion driven by dark energy, from the structure of space-time to the existence of unseen particles, reality operates on levels we are just beginning to understand. We've discovered that most of the universe is invisible to us. Dark matter and dark energy make up 95% of its content, that the remaining 5% behaves in ways that challenge classical logic. We've realized that space and time themselves may not be fundamental, but emergent from deeper informational or quantum structures. We've seen galaxies form sooner than expected, black holes merge and ripple space-time, and ancient light from the Big Bang still bathing the cosmos in a cold, persistent echo. Every one of these discoveries reminds us the universe is a living mystery, one that constantly evolves the more we try to observe it. Second, our models of reality are both powerful and limited. General relativity and quantum mechanics are two of the most successful theories in the history of science, yet they refuse to unite into a single coherent framework. Efforts to bridge them, whether through string theory, loop quantum gravity, holography, or emergent space-time, are imaginative and profound, but incomplete. Some theories predict infinite universes. Others suggest we're living in a simulation. Still others propose that time itself is an illusion. The sheer diversity of possibilities suggests that the true nature of reality may be stranger than we've yet dared to imagine. And yet, rather than frustrate us, this realization should inspire us. It reminds us that truth is not something we inherit, it's something we pursue continuously, courageously, and collectively. Third, we are not observers standing outside the cosmos, we're participants within it. The atoms that make up our bodies were forged in ancient stars. The thoughts that pass through our minds are shaped by the laws of the same universe we seek to understand. This connection is not just physical, it is existential. The universe does not simply surround us. It flows through us, animates us, and awakens in us the capacity to question. Our ability to wonder, to calculate, to explore, to dream, that is not incidental. It is essential. In us, the universe becomes conscious of itself. And that fact carries deep moral and philosophical significance. It means we are not insignificant. We are meaningful, not because of where we are, but because of what we can ask. Fourth, the journey is the reward. In seeking to understand the cosmos, we discover not only the stars, but ourselves. Science is more than data and formulas. It is a story of becoming, of evolving from superstition to knowledge, from fear to understanding, from isolation to connection. It is a practice of humility, curiosity, and hope. Each mystery we encounter, whether it's the true nature of dark energy or the question of whether time had a beginning, is a chance to stretch the limits of our comprehension and compassion. It teaches us to think bigger, to feel deeper, to act more wisely. Cosmic exploration is not just about reaching further into space. It's about reaching further into what it means to be human. And finally, the infinite possibilities of space reflect the infinite potential of our minds. The universe may be endless. It may contain multiverses. It may be a simulation, or a dream, or a hologram, or something else entirely. But within that uncertainty lies possibility. Each unanswered question is an open canvas. Each paradox is a seed for a future discovery. In the vast silence of the stars, we are not lost, we are invited. Invited to wonder, to learn, to connect, to imagine. The infinite is not a void to be feared. It is a playground for thought, a cathedral of reason, a temple of awe. So should the mystery remain open? Yes, because in openness lies growth. In questions lies courage. And in the vast, beautiful, mysterious unknown, we find the space to become more than what we were. Not just smarter, but wiser. Not just more advanced, but more aware. Aware that we are part of a cosmos that is not finished. Aware that truth may not be singular, but layered, unfolding with every generation. Aware that we are, in a very real sense, the eyes of the universe, gazing back upon itself. In the end, the stars will continue to burn. Galaxies will continue to drift. The universe will continue to expand or contract or cycle or stretch beyond comprehension. But we brief, curious, brilliant creatures will continue to ask. We will continue to explore. We will continue to reach. And that, perhaps, is the most beautiful truth of all.